Hello, and welcome to this presentation of the Introduction to VHDL and Vivado for COMP3222. This is optional content, and it's only needed for those students who wish to know a little bit more about what's going on behind the scenes for the Vivado environment, the basis board, and the VHDL language. However, it's not required for the course or for the labs, only for those people who wish to add a little extra information. We'll be using the Basis 3 board. This is a board by Digilent, the company who created it. It has a Arctic 7 FPGA, a 7-segment display, switches down at the bottom, LEDs above that, and a 5-button keypad, which we will all use in the course. Also, the power switch is right here, and the power needs to be set to USB power for the labs to move forward. There are a number of features on the basis board that will not be needed in the labs, but here's the complete list from the Digilent website. In particular, at the center of it all is the FPGA, which we will import our designs into. It's the Xilinx XC7A 35T 1CPG236C. That full part number is actually important because when we do FPGA designs, we do not create for a class of chips, but we actually compile the end bit stream for a specific chip on a specific circuit board. So the complete part number is needed at the very first setup for the program. The FPGA isn't the only thing on this board. There are a number of other peripherals, including a USB programmer, some flash memory, VGA port, push buttons, LEDs, slide switches, and a 7-segment display, all of which we will be using, as well as a separate microcontroller, this PIC24F, that can interface and simulate a USB HID class device. The human input device class is the class of USB drivers for keyboards, mice, and a few other very low-speed communications protocols. However, we will not use that, and instead we will focus our USB effort only on the programmer. The programmer is here on bubble number 13. The HID device is over here on number 11, but we will only use number 13. All of these peripherals talk directly to the FPGA chip in one form or another, and it is our job as digital designers to create a design that supports all of those types of peripherals. Programming of the FPGA itself is done through the Vivado design environment. It is pre-installed on all of the lab computers in a virtual machine, which you'll work on in lab on week 1. However, if you wish to download your own copy of it, it is available at xilinx.com/support/downloads. You will have to register for an account. It's free, and you can use your UNSW account as part of the registration. When you get to the download page, there are a number of versions available to you. We will only use 2024.1 in this course. The Vivado environment is not backwards compatible, and so downloading a future version will not allow you to create submittable code for these designs. So the lab demonstrators may require that you resubmit, and possibly you might be late because of that, simply because you did not follow the instructions in the lab. So always download the correct version, 2024.1. Note that these downloads are very, very big. The Vivado environment is over 200 gigabytes if you install all the components on there, which are not required for any of these labs. So get the correct version, download it once. It takes about 3.5 hours to download and install when you're on the university network, which is fairly fast compared to home networks that can be well over 6 hours to download this. So download and install them from the campus network. The installer is not very big, but it will connect to the main server at Xilinx and spend 6 hours installing. Make sure that you have enough space for it. Also remember that your lab demonstrators cannot help you with the versions that are not 2024.1, and Vivado is only designed to work on Windows and Linux computers. The Mac versions of it do not work, and they generally work after they fail to work after about the second or third time you try to use them, and your demonstrators cannot help you with Mac stuff. So get used to using the lab computers. That's where the quiz and the midterm and the exams will be done anyway. So spend time in the lab. Once you have the Vivado software, you can connect to your Basis board using a USB connection using the programming interface. On the board itself is a programmer called the FTDI chip, and the FPGA itself communicates with that. So this is where the USB interface meets the FPGA using an interface known as JTAG. The Vivado IDE is fairly comprehensive. It's used as the standard tool for all of the Xilinx and AMD chips, and there is no open source equivalent for it because it's all proprietary techniques. So let's take a look at the Vivado environment. The IDE itself can be started using the Windows desktop icon if you're working on the lab computers, or if you've installed it on a Windows laptop or home desktop. If you have Linux and you've installed on a Linux environment, you need to do two separate steps. The first is you need to source this settings64 shell file in wherever the installation target was. Settings64 will create environment variables and some symbolic links that are temporary so that the current version of Vivado, so the correct version of Vivado is run every time. Once you've run that settings thing, which has no output, you simply type the Vivado command to run the GUI. The GUI itself is the main IDE that we'll work with in this project, in this course. There is a project manager or a flow manager along the left-hand side. This is essentially a series of steps that we will run as we start a new project all the way down to running the design that we've created on the actual hardware. There is a sources window that tells you all the source files. And there is over here, and it says project summary, but this is usually takes up most of the screen. This will be where we will either see simulation waveforms or where we will see source code. Down at the bottom is the logging system. We can see any design compilation or implementation or synthesis steps that are in progress down here. So this is code that's being evaluated, synthesized, implemented. And then a logging tab, which will tell us the standard output or logging messages of each one of those commands. The workflow for Vivado is long but fairly straightforward. And it's very different from what you would see in a compilation of something like C or C++ or even Rust, Java, or any of those things. We will begin a project with the project setup, where we define the specific processor or FPGA and the package that we will use. Remember that these types of designs are very tightly connected to the actual circuit board itself, and so knowing the exact chip down to the actual package and number of pins and speed grade are all important. So we define that in the very first step. After that, we will connect physical pins and external timing constraints using a process known as a constraint file. This is where we map signals that are inside the FPGA code base into physical pins on the circuit board to make sure that the correct logic goes to the correct device on the circuit board itself. You can create both of these things from scratch. In this course, we will use a predefined board support package. However, in the real world, for a new FPGA design, you would actually have to define these yourself. The source code is, of course, where we define all the logic behavior. These are VHDL files. And this code system is quite a bit different, again, than other programming languages, and more about that in a little bit in this presentation. But this is where we define the logic behavior of the actual design. Synthesis is the first step where we go from a text code based description of the design into the logical or the gate or transistor level description. This is known as the register transfer layer language, and in the synthesis step, we've converted our VHDL code into basic logic primitives: AND gates, OR gates, flip-flops, wires, etc. After synthesis, we generally will run a behavioral simulation. This is where we will create a test file to simulate the outside world and verify whether or not our defined logic, made here in the source code, in fact behaves correctly. After we're happy with the code's logic, we begin to move on to the first of our detailed synthesis steps, or implementation steps. The implementation step first converts the logic primitives into lookup tables, which are our main way of creating new logic that's programmable. And then following implementation, we begin to allocate those lookup tables into specific chip locations and work on the wiring in between them. Finally, with the lookup tables in place and their wiring established, we are now have a complete enough design to do timing information. And now we get to see whether or not the logic functions in the time constraints needed. For example, the clock or delay characteristics that the board needs. After after place and route, we end up with an intermediate language representation of the whole design. This is essentially a database of logic locations, lookup table values, and interconnects. It is not yet suitable for placement or for saving onto the into a file, and so the generation of a bitstream file is where we take that intermediate representation and create a single file that has the attributes needed for programming the chip itself. Lastly, our final design bitstream is programmed into the device. In this course, we will run those design files directly on the chip. The bitstream will run directly on the chip. In a production environment, we would program that onto flash memory so that as soon as power is applied, the FPGA gets its bitstream is configured right away without the need of a computer. So let's take a look at some of the steps of that workflow, which, by the way, of course, has errors and will have some sort of loop that goes back. Importantly, simulation at these two steps is very, very necessary for production design because changes to source code have to waterfall all the way down. Remember that the place and route, implementation, and synthesis are global operations. We are globally optimizing the entire program and the entire design on the circuit board. So a change to the source code has to propagate back through all the steps over and over again. We cannot do a great deal of partial logic that will be reassembled at the end. The optimization is not sufficient for that kind of thing. Most projects will spend most of our time on the source code editing step. In this case, Vivado comes with a context-aware text editor built into the IDE and a bunch of code templates for a lot of useful VHDL coding functions. This is what the IDE looks like in source editing mode. You can see it's got syntax coloring, it's got line numbers, it's got code folding, and a few other things like that. You will quickly realize that this is not quite as good as a more sophisticated editor such as VS Code or even Emacs. However, this is what your demos will be able to help you on, and so using those other coding environments and then trying to bring them back into the Vivado environment is actually quite a bit of work. So at the very least, I would work mostly with this IDE. You can save files into source control using Git. Remember that the lab virtual machines will wipe their own memory every time you log out. So Git or a shared network drive are both suitable ways to keep your source files intact as you move in and out of the lab. If you choose to use Git, make sure you capture the XPR file, the VHD file, and the constraint file, the XDC. VHD is your source files, and XPR is the overall project file. Another practice that's also very safe is to create an archive zip file. In the case of an archive file, we do not want to create the zip file directly. Rather, we want to use Vivato's built-in archiving capability, which is located in the File menu, Project submenu, and then the archive. This will create a zip file. However, it also strips off a lot of metadata. It makes the code portable from one system to the next, and it is the way that we will be submitting all of the labs into the Give system. You use the archive function. One nice thing about the Vivato IDE that's not available in a lot of other IDEs, including VS Code, is code templates, sometimes known as the light bulb button. Here is the IDE again, and you can see a little light bulb icon here, which when you click on it, will give you a pop-up menu for language templates. If you want to, if you cannot remember the style of coding for a particular construct, such as entity declaration, component instantiation, or whatever, you can simply type that into the search feature and you will get a preview of what the grammar would look like. There are a number of placeholders in there in these angle brackets where you would fill in the details of your code, but you can copy this and paste it into your code, make the changes to the angle brackets, and feel fairly good about your the grammar of your code at least working out pretty well. Note that there is a Verilog code template as well. We will not use Verilog in this course. This course will focus on the VHDL language. And so make sure you're looking in the right area for the code. Now, synthesis is the step which is similar to but somewhat distinct from compilation in a C or C++ program. In this case, what we're doing is converting the code in VHDL form into traditional logic gates and some other primitives. We run the synthesis step simply by, in the project flow navigator, clicking on the Run Synthesis play button. You can see the number of synthesized designs that are currently in progress. Here in the design runs area, there's a status column. And you can also see implementation, our next thing. Here you see that nothing has been started. Synthesis is generally a fairly fast process. If you wish more detailed logging information, you can, down at the bottom of the IDE, you can click on the Log tab. There's a synthesis button that's been clipped off here. This will give you essentially the standard output of the synthesizer as it goes through and begins to establish what you said in VHDL and how it is going to actually replicate that logic using primitives such as lookup tables, buffers, arithmetic units, and so on. Implementation is the next step in bringing your design to reality. In this case, we take that synthesized traditional logic and add a constraints file to it, which gives us timing and pinout information to create an optimized logic for your design on that particular chip. Later on, we will take that optimized logic and allocate sites on the chip that will hold that logic, as well as the interconnection between those sites. This is known as placement and routing. This process can be quite iterative, where allocated sites and interconnection do not meet the timing demands of our constraints file, and so we have to recursively optimize over and over and over again until the place and route is satisfied with the constraints have been met. This is by far the most computationally expensive process in RTL designs in FPGA synthesis. And so you can wait on a large design quite a few minutes for this process to go through. It's not highly parallelizable. And so multi-core processors and GPUs and other things like that really don't benefit from this step. This is a very slow algorithm because it is a global optimization. And of course, implementation is simply run by the Run Implementation Play button. And as you can see, the Flow Navigator is moving down from the top into synthesis, implementation, and further down. So you can see the Flow Navigator is a sort of a script that, or a plan go from top to bottom as we complete the design. The implementation, because it can run so slowly, is often an area where you want to check on the progress. Here you open up the log, make sure you click the sub button for implementation so that you're looking at the implementation outputs, and you will see a number of phases as it goes by. Phase 1, phase 2, phase 27, and it may regress back to phase 2 again, or phase 4, or whatever, as it's ripping up logic and finding better routes. Once we have the intermediate representation in the form of sites and their interconnects, as well as the lookup table configurations that came from implementation and place and route, we are ready to generate the bitstream, the final file that can be stored on a drive or put onto a flash memory to actually run the FPGA design. There's a button for that, cleverly called Generate Bitstream. It's located inside the Program and Debug area. You will only have to generate the bitstream once. Every time you make a change, you will have to generate it over again. In the case of the bitstream, what we're doing is we're taking those sites that were allocated in the interconnection and making an executable file, or a programming file. Once we have the programming file, we can begin to actually program the FPGA itself. In this case, we would connect to the basis board in the same way we had mentioned before, using Vivado via USB, the FTDI chip, and then that connects into the FPGA itself. This is found in Vivado, right below Generate Bitstream, in a tab that says Open Hardware Manager, and specifically the step of Open Target. There is could be a number of things on the USB or even on this programmer to FPGA chain known as the JTAG chain. And so there's a separate step that says auto connect to the target. This will automatically connect to the first FPGA that it finds, which is generally what we want. After that, we can right-click on all the devices that are found on the programmer's chain. We can right-click on the XC7A35 and find the program device command, and this pop-up will pop up to tell you the to ask for the bitstream file. Generally, the bitstream file is automatically populated for us, and if we're happy, simply click the program button. The programming file, the bitstream file, is actually put onto the FPGA via USB at this point, and the program is run. There is no boot up, there's no reset, nothing needs to happen at this point. The program or the design that you have captured is now ready to go and fully running. Remember that for this style, if you unplug the FPGA board, or if you lose power or something like that, you will have to reestablish and program again. All right, so that was the Vivado environment. The other thing that is sort of new to a lot of us is the programming language itself, VHDL, which you will be exposed to in the very first lab. Here we'll just talk a little bit about the basics of this language. VHDL is actually an acronym with an acronym inside of it, which stands for VHSIC Hardware Description Language. VHSIC stands for Very High-Speed Integrated Circuit. So this was originally developed for designing integrated circuits. The language was developed long before the idea of programmable logic in an FPGA actually existed. To take a look at VHDL code, let's talk about the code structure at this point. You will learn much more about the language as further labs go on. But the code structure is based off of a root language known as Pascal, which was very popular as a teaching language in the early 1980s. And many of these tools were developed in that same time frame, so Pascal was one of the most robust languages of its time. It had a derivative language known as Ada, which was for real-time programming. And both of these have the same basic syntax and root. Unfortunately, nowadays, Pascal-derived languages are not as popular, and so we don't see the likes of them, which makes the grammar a little foreign for those of us who grew up with C, C++, JavaScript. Even Rust has kind of the same basic root language, and we're all familiar with Python by now, which has a different root language. So the Pascal language begins with libraries clause at the top of the program, which bring in new packages from other programs that you've created in modular fashion. We will have an entities clause that will create the basic signature of the top level module that we're trying to program. This will have definitions of ports, which are input and output signal connections, and generic, which are sort of template parameters if you think of the C++ standard template library. We will have an architecture clause, which is one of many, perhaps, architecture clause. And architecture is simply the code body of how the entity will be implemented. The architecture will have any signal definitions of signals that stay within the module. So the ports will be signals that go in and out of the module and connect to other modules, but the architecture signals will be internal. We also have any custom types. VHDL is an object-oriented language. We can create custom types with structures in them. And any external or subcomponents that this particular implementation will use will be declared here. And of course, we'll have the code body itself where essentially all the logic takes place. The code body is also the place where any components that we've declared might be invoked. So this is where we instantiate any components or entities that were defined elsewhere. So think of this as using subcomponents, and here we are simply declaring what those subcomponents will be. It's always dangerous to draw too much equivalence between Pascal languages like VHDL and their C++ equivalents, but this is a very, very rough similarity. Don't take this too seriously. Essentially, libraries are a lot like an include statement in C++. Entities are a lot like the top-level prototype, like the main prototype. Ports and generics are a lot like functions parameters. So think of, main having the argc parameter and the argv parameter. So those would be like two ports, as well as any parameterized macros. If you've worked with the standard template library in C++, this is very similar to what a generic would be as a template parameter. The architecture clauses are the function body. So remember when you create a two-part class in C++ where we have the class header and then the class body, this will be the function body. So this is what the architecture is. Signals are very, very badly associated with variables. Signals are very badly associated with variables, but they're the closest we have. Custom types, of course, are a lot like inline classes, and component declarations are a lot like inline prototypes. In particular, there's not a whole lot of similarity in the code bodies because RTL languages like VHDL are not procedural languages like C++ and Python and a lot of other things are. However, entity instantiations or component instantiations are a lot like object construction. You're essentially saying, I'm now going to make an object of this class, and its object name is going to be such and such. That is an entity instantiation. Another way of looking at the two languages is to look at the actual syntax of the code. Comments in VHDL begin with the double dash. Libraries have two parts. You'll have a library name that brings the entire library into the scope of the current module, and then a use keyword to take that library and add individual packages. Oftentimes these libraries will have many, many packages in them, and so we only want to use one of them. Entities are a lot like a function prototype. Here's a function prototype with a void and nothing going into it. It's not quite a function because this is a pretty bad similarity, But the entity clause looks like this. We have the keyword entity. We'll have the name of that entity, which is called Blinky in this case, a keyword called is, followed by the ports and generics. Then we will end the entity by ending it by its name. So entity Blinky, end Blinky. Entity Blinky is, end Blinky. All right. Architectures are, of course, the code body. Architectures have a syntax that has the keyword architecture, the name of the architecture, followed with the word of, the name of the entity it is going to be specifying, then an is statement, and then an end. So architecture, this one's called arch of Blinky, so Blinky was an entity. So we're saying this will be the details of Blinky, is followed by a bunch of stuff, and arch. Now what goes on in between is signal definitions. The local definitions will be done here, followed by a begin statement. The begin statement is where we start to, that's the beginning point of actual code that will be the logic of the module. So here we're simply saying there are going to be some signals, some types, etc. And here we're going to use them. Now, a signal is a logic line that has timing information and a measurable state. Unfortunately, there's nothing quite like that in a high-level language, but this is the syntax. We have the keyword signal, followed by a name, colon, and a type. In this case, the type is standard logic, which is Boolean logic plus some extra stuff. In contrast, a variable is a macro-like, non-timed, temporary name. I say macro-like because when we create a change to a variable, it does not propagate from one time instant to the next. So remember that variables are not the primary tool that we will use in these kinds of languages. We will mostly do signals. In fact, almost all of our work will be done with signals. However, if you need to use a variable, we use the keyword variable. V is the name, colon, a type. This one's integer. And then this one has a default value of 100. If we wish to change a signal, we do what's called an assignment. This sets the value of a signal. Unfortunately, again, there's nothing quite like this in a high-level language like C++, but the syntax is simply to take the signal name. We will use this arrow operator, which is a less than followed by an equal, so you can think of it as a left arrow, and then an expression, in this case, not my wire. So what this is saying is assign my wire the value of not my wire, flip its logic. Assignment of a variable is syntactically very similar. In this case, rather than using the left arrow, we use the colon equals assignment operator. In VHDL, a single equal sign is used in Boolean tests. So if A equals B, as opposed to if A equal B. We will just use single equal, and then we want to make it, if we want to make a change, we will use either colon equal if it's a variable, or more commonly, most all the time, we will use an assignment like this. Just a foot stomp again, variables versus signals. Variables are macro-like. They are temporary names. They do not last beyond clock events. So think of, I say macro-like because what you want to think of is every time you change a variable, whenever you would use that variable, you would simply copy and paste that expression, not the value. So this can get people into a lot of trouble. Rarely will we need to use variables. Signals are our primary way of holding information. Signals have the ability to store states between events or between timing changes, so a clock shift. And signals can update after the last delta. So that means that if I set a signal, I may not be able to get that until the next clock cycle. This has to do with how it is actually going to be implemented in hardware. So let's take a look at Lab 0 and walk through the program. We won't go through much of the logic of why it's going to do what it is, but just look at the program structure. This is the code of the first blinking program. You can see we have a library import. The library is called IEEE. it is using two separate packages, standard logic 1164 and standard logic unsigned. The standard logic 1164 is where we get most of our Boolean stuff, and as you might expect, the unsigned library is, or unsigned package is where we would get integer stuff. So the ability to add numbers, for example. We also have an entity declaration. In this case, the entity's name is Blinky. And here's entity Blinky is some stuff and Blinky. That stuff is two ports. That is external signal connections. One is called clock and one is called LED. Clock is an input, LED is an output. That means that this module will eventually route clock to a physical pin and LED to a physical pin because it is the top level module. The architecture definition is, as you might expect, architecture. This one's called behavioral, and behavioral down here. And the entity that it's architecting is Blinky, the entity defined up here. We have two signals, a vector of 26 bits, that's called the count, and you can see it's got an initial value set to all zeros, and an OL. These are both standard logic. One is a scalar standard logic and one is a vector. And you can see that this number, which is what it will eventually be, is in binary form. We have some logic, combinational and sequential, both of which will be defined later. And that's it for this. To contrast that, another type of program that we will use sparingly in this is the test bench. The test bench is just a VHDL program like anything else, except it is simulating the outside world. Whereas Blinky here needed two inputs, a clock input and a LED output, so two ports. The test bench has no ports because it is simulating the outside world. Okay, so it itself does not have anything else. What we will do in this is invoke a component and build a simulated clock and test the LED output later on. But the code looks the same. A library statement. Here we use the 1164 logic only, and we've added a new library called standard, which has a standard environment package. We have the entity itself, no ports because it's simulating the outside world, so it itself does not connect to the outside world. The architecture, of course, itself. The signal declaration. Here we've created the signals that will be needed by Blinky later on. And two process loops. One to simulate the clock and one to do the logic itself. We've also given a hint to this module of what Blinky as a component will be like. This is known as a component declaration. We are telling this module that there is some component out there in another piece of code. Its name is Blinky, and it has two ports. Notice that the syntax is a little bit strange here. Component, Blinky, and component, which is slightly different from architecture, behavioral, and behavioral. This was a name and name. This was keyword, name, and keyword. So you can see how this can be a very confusing area. That's why the code template in this IDE is very valuable to you. You don't have to worry about a lot of this stuff. Okay? Once we have the component declared, we can then invoke it, right? We can create an instance of it. Here we are saying Blinky is now used. We are going to map the signal LED to the signal LED. So this port LED is mapped to this signal, and the port called clock is mapped to the clock. And the name of this is device under test, or DUT, a common name for test benches. So you can see the basic test bench code is essentially simply create a component declaration, create the signals that that component needs, simulate what those signals are going to do, and then instantiate the component that you're testing. A couple of gotchas with the language always seem to affect people. One of them is a misplaced colon, semicolon, or comma. Like any other language, However, VHDL can be quite tricky in exactly how the semicolons and commas and so on are going to do. It's not always intuitive without the full Brachesnauer form of the grammar, which we won't cover. Forgetting to put those begin and end statements in the right places catch people quite a bit. If you create a begin statement with a label, then you have to end it with that label. And a big one is the use of variables instead of signals. We will almost always need signals, not variables. Another thing that catches people is the use of loops. Synthesizable code that goes on the FPGA cannot use loops. Not for loops, not while loops, not lots of different loops. You will learn in this course a different programming construct that gets you out of the for loop, the while loop, and all of those other looping constructs. And of course, AI-generated code is rife with the misuse of labels and the use of loops. These last two always seem to pop up in AI-generated code, and you end up with code that cannot actually fit on the FPGA. These programming constructs are not available in the actual code. All right? So work more with your demos, work less with the AI-generated code. With that, I hope this has been illustrative for those people who want to see a little bit more about what's going on there. We're happy to tell you more as we have free time in the demo class and as we help people out. All right, with that, happy coding, and I'll see you in the lab.